Welcome to another short and sweet lesson on physical science and physics. Today we're dealing with one-dimensional motion. If you've not read this book, Cartoon Guides to Physics, or seen it or taken a look at it, it might be worthwhile for you to take a look at all or part of it to help fill in what the book doesn't fill in. So we're going to go through a few examples today, and hopefully some of the stuff in this will also help you. For those who've never taken a look inside the Cartoon Guide to Physics, it does have some very nice pictures and some simple explanations that help spell it out. Today we're talking about motion from the chapter 1, and you can see the different pages. If you've not seen them before, you should see them, but now you can't say you haven't seen them. And these brings up many wonderful, great concepts, such as gravity makes things go, and that we can predict where something's going to go if that's going on. So in this case, this also gets back to what causes motion is the application of unequal forces. In fact, they're right there. So force are associated with acceleration, which is a basic concept that you need to have. And now we're going to go through doing a couple of problems step by step. Well, as promised, we have how to solve some problems. Let's first break out what are the steps. First step is, what is the real question? Not just what is the question, because sometimes you have to do a little bit of digging into the question. Because if I were to say somebody went jogging from their house at 5 miles an hour for 1 hour and got back home at the end of the hour and said how far they go, well, one interpretation is they started at their house, they ended at their house, they went 0. The other person somebody else might hear that question and say, well, if you went 5 miles total, 5 miles an hour for 1 hour, that's 5 miles. And the third person says, yeah, but they went 2.5 miles away from their home and then came back, and they might answer 2.5. Now, who's wrong on that answer? So sometimes questions need to be clarified, because from just a simple statement like I said before, you could end up with 3 different answers. The next one is, what is given to you for free in a problem? A lot of times that comes from our frame of reference aspect. When I tell you we're starting on Earth, and to assume certain things if I don't tell you, such as if I don't tell you the starting time, assume the stopwatch started at 0. If I didn't tell you the starting position, you can assume we started the ruler at 0. If I don't tell you the initial velocity, you can assume that it started at rest. And you assume the acceleration's constant unless I tell you otherwise. In fact, in this class, we probably will have very little, if ever, see a non-constant acceleration for a problem. Then you say, what are the mathematical representations that go with the different interpretations? Well, the basic mathematical operations are these. These relationships explain how we can put a number on what's happening in nature. Speed or velocity, since we're in one dimension, is your change in distance, and this velocity be change in displacement, over time. Velocity averages, well, one way to do it is to add up the velocities and divide by the number you have. The other one, the short version, is we're usually going to have a final velocity and an initial velocity. That's 2 of them, so add them up, divide by 2. Gives me the average, and I can mix and match these because this is also an average velocity. So I can substitute one for the other. My final velocity would often be how fast was I going when I started, plus how much did I change my velocity and for how long did I change it? Acceleration times time. How far did I go? Well, that would depend on where I started. Was I moving? If I was moving initially, how much time was I moving initially for? Plus, how much did I change my velocity multiplied by the amount of time squared? Here's what it looks like in a math formula. My final position is my starting plus whatever movement I had multiplied by the time we moved plus the acceleration and the time that the acceleration was applied. Now these are the same t because I start with the velocity and start pushing on it to either make it go faster or slower. And then we have one last version where there's no t. My final position, or my final velocity squared is equal to my initial velocity squared plus 2 times the amount of acceleration applied to my object multiplied by the distance we did it for. And of course you can rearrange this quite a bit, and this becomes very helpful as well. Those are the relationships. That is number 3. And can I combine known relationships or delete stuff out like we did when we did the drop the rock off the cliff example? So with that in mind, let's take a look at making a check sheet out of this so we know what we started with and know where to go with. So we could go for a couple of examples here. Say for free, I give you that we had a change in time of 10 seconds. And I tell you in the problem that UE went 20 meters. Doesn't sound like, it looks like you have a lot of stuff you don't know. But on that note, what else was given to you if that's all you were given in the word problem? Somebody traveled 20 meters in 10 seconds. Since I didn't tell you what the initial time is, you can assume that's 0 seconds. The initial distance on the ruler would be 0 meters. The initial velocity would be 0 meters per second. So from the 2, I have 5 items that are known. Now from there, I can start saying, okay, what can I do very easily from my math formulas? Well, looking at the formulas down here, let's look at the first one. Velocity averages is distance over time. Do I know distance? Yeah, I know distance. Do I know time? Yes, I do. Also, as far as doing computations, do I know what the final distance is and what the final time was? Well, the change in distance was minus 20, which is equal to final minus initial. Because delta equals your final value minus your initial value. Well, looking at this, I had 20 to start with. So 20 meters minus my initial 0 meters equals 20 meters. So while it doesn't seem like much, I can, of course I think I did that a little bit wrong. Yeah, it should have been 20 equals final minus initial. This was 0, this was 20, this equals final. I can subtract this from both sides, so 20 minus 0 equals final. I get the same math. That's what happens when you do things in your head. So over here we have position would have been 20 at the end. Using the same process for time, delta t equals t final minus t initial. Yes, I keep changing letters so you can see that the letters change and you get in the habit. So delta t plus time initial equals time final. Delta t was given as 10 seconds. So I put in 10 seconds plus 0 seconds equals 10 seconds. Now some of you might say, well, that was some pretty simple addition. These problems are that simple if you let them be that simple. We still don't know what the average velocity is, so now we can go again and we can say, okay, delta V, or actually just V average, equals the change in distance over the change in time. Well, we have a change in distance of 20 meters. Change in time, 10 seconds. 2 meters per second. Over here, velocity change in velocity average was 2 meters per second. Change in velocity. Once again, delta V equals VF minus VI. Do I know what that is? Not yet. I also know that velocity average equals V final plus V initial over 2. I want this, so I can say 2 times velocity average, because I multiply both sides by 2, equals velocity final plus velocity initial. Subtract velocity initial from both sides, and I end up with 2 times velocity average minus the initial velocity is equal to velocity final. I have that up there, so 2 times 2 meters per second minus 0 meters per second equals 4 meters per second, which is equal to velocity final. Come over here. Oh, we were using blue for the computed, so 4 meters per second. Now, change in velocity. Can I figure that one out? Yeah, I should be able to. Doesn't sound like it should be that difficult of a math equation. Delta, let's see if I can write a triangle. V equals VF minus VI. Well, VF is 4 meters per second minus 0 meters per second equals delta V equals 4 meters per second. Now you're probably going to notice that my deltas and my finals are the same number, and that happens often when you have the initials as 0. So if you can set the initials up to be 0, you'll suddenly find, hey, wait a second, I do half of this in my head because I can remember the relationship. Last thing we need to figure out was acceleration. Acceleration is, by definition, change in velocity over change in time. Do I know a change in velocity? Yes, I do. Meters per second. Do I know a change in time? Yes, I do. 10 seconds. I do this, and I end up with 0.4 meters per second squared. And that's it. So ask any questions when you have them.